Hello everyone, welcome back to the ECE 475 HFSS second tutorial session. In this tutorial session, we will take a look at how to create a fundamental 3D models in HFSS. We will see how to design and simulate electrically small loop antenna, and I will show you some tricks in plotting 3D radiation fields. Now let's go to the HFSS and see how to create these fundamental structures or 3D models in HFSS. We can easily modify them, and we can easily parameterize it by modify them by input parameters to these structures, and modify every structures you want, like these pictures. So let's go to the HFSS. In HFSS, you can draw a box like this. You can draw a cone. Also, you can draw a cylinder. Or you can draw a sphere. Or you can draw a regular polyhedron. Easily you can set the segment number, let's say 6. Also, you can draw a torus. You can draw a bond wire. For a bond wire, you should define the line and a start point and end point of this D and distance. Also modify the diameters of the bond wire, H1 and H2, the distances, and the D, and whatever. By pressing Ctrl Alt and dragging your mouse, you can see the bond wire you create. Now let's see how to define a helix and spiral structures. For helix or a spiral, you should define first a rectangle shape like this, and by click on this and using the draw a helix, first you need to define the axis to this sheet or this helix. Let's say equal y. By pressing Y, you can modify the axis. You can see the pitch, and you can modify the pitch and turns of this helix. You can easily define a helix. Also, you can, for example, by drawing a circle, and defining the axis. You can, let's say, 0.5 and 5 turns. Oh, what's happening? let's say that's good. Yeah, you can create a spiral. Also, you can create a shape by sweeping the sheet, a sheet or rectangle sheet over a long axis to create a shape you want, like pressing, drawing some rectangle sheet, and by sweep it along the vector. This circle means that you are in the middle point of this rectangle, and by pressing Z you can create this. In this way you can create a box, and if you put the angle to this sheet, like using a sweep along a vector, going to the middle point Z, for example 30°, you can create this kind of cone. Also, we can create shapes by sweeping the 2D circle along or around this axis, around the defined axis. Let's say X 270 degree along the x-axis. Okay. Now we can see how to create this shape. You can also define, for example, draw a polygon. Let's say 5, and draw a line. Let's say in X, Z plane. Draw a line. Also, we can, by creating this, sweep along a path. This polygon sweep along this path, and you can create this shape. It's so funny. Now let's move on to design electrically a small loop antenna in HFSS. As you can in a figure, the electric small loop antenna, the circumference of this loop should smaller than lambda divided by 10, and for electric large loop the circumference is in comparison with lambda, it's equal to lambda of the frequency of the antenna, which lambda is the wavelength of the lower frequency of the antenna, operating frequency of the antenna. As you can see in the figures, the electric small loop antenna and the infinitesimal electrical dipole antenna are dual to each other. In both cases, we suppose that the current along the wire is constant, so in the calculation of the electric field in a far field region, and we can easily find the far-field electrical and magnetic field in both cases. You can find the theoretical calculation of this electric field and magnetic field in your references like Balanis or Collins, or in your Professor Ramahi's note in the antenna lectures. Here we just summarize the concept that the electric field of the small electric current loop is equal to the magnetic field of the small electric dipole, and the magnetic field of the small electric current loop is equal to the electric field of the dipole in a far-field region. So they are dual to each other, and as you can see in these sentences, the E theta is equal to in a far-field region J eta K I naught delta L, which is the electric length of the dipole, small electric dipole, EJKR, and the sine theta, multiplied by sine theta, which is the pattern of the electric field in the theta direction in the far field, and H phi is equal to JK I naught delta L divided by 4 pi R E minus JKR sine theta. And you can see a small electric current loop, electric field and magnetic field in a far field region, which the H theta is equal to the E component in electric dipole. These two sentences are equal together, and E phi and H phi are equal to each other in the far field region. As you can see, they are dual to each other. Electric source is changes to magnetic source. E is changing to H. H is changing to minus E. I naught is to changing to magnetic current. K is equal, and eta is changing to 1 divided to eta. So they are related to each other. For example, let's say delta L is equal to 6 centimeter, and B, the radius of this torus, is equal to 9.5 centimeter. We know that the lambda for 1 megahertz is equal to 300 meter, for 10 megahertz is equal to 30 meter, and for 100 megahertz is equal to 3 meters. So let's say this design is for 100 megahertz, and so delta L is divided by lambda is equal to 0.02. So this dipole is electrically small because it, in comparison with the lambda, it's too small. And for B, the radius of the torus and this loop, in comparison with lambda, is 0.032, which is very small, and it can be negligible. So this electric small dipole antenna and current loop magnetic dipole antenna can have a feature of this antenna, because in comparison by the lambda, they are too small. Delta L for the electrical dipole, it's too small, and B is too small from the magnetic dipole. As we know, the current is constant. We assume that the current is constant in the small loop antenna. B is the loop radius, and A is the wire radius. Here is the finger rule that the circumference of the loop antenna it should be smaller than the 0.2 lambda. So we can say that the loop radius should be smaller than 0.032 lambda. Now we are going to HFSS and design an antenna and see the far field pattern and radiation pattern of this small loop antenna, and let's move on. To create a small loop antenna, there are multiple and several ways to create a simulation model for this loop antenna. First of all, it's drawing a torus. The second way is sweeping a circle around a circular path or subtracting to a circle. Here you can see how to drawing a torus. You can modify the center position of the torus, the axis of the torus, and minus radius and major radius. This minus radius of the torus and the major radius of the torus. Or you can sweeping a circle around the circular path. You can define a circle sheet and then sweep it around a circular path. So you should select your surface and pass together as I indicated in the past slide, and then select to sweep along the path. Or you can subtracting two circles. You can define a one circle, a bigger one, and then defining a smaller one, and then subtracting from these two one together. Let's see this, and subtracting the port position. Let's go to HFSS. Let's move on to HFSS and see how to create these features. First of all, defining a torus. You can define a torus. The center position, the axis of the torus, the minor radius, and the major radius of the torus. Or you can define a circle. You can draw a circle in, let's say, in XZ. And also you can define an arc, or you can sweep around the axis, let's say Z axis, to, let's say, 330. We have a very nice small loop antenna. Or you can define two circles. Let's go to the XY plane, the bigger one and the smaller one. We can easily subtracting two by selecting together and subtract. Circle 1, the bigger one, minus circle 2, the smaller one. Now we can sweep it along a vector like Z to get it a thickness like by pressing a Z we can have a thickness in the Z direction and 0 draft angle. So again we have a nice loop. Now we can define a port position, and subtracting the port position from this small loop antenna, we should notice that we should keep it reasonably small, this port position. As I say, we can have a thickness and sweep along the Z direction to give the circle have a thickness, and we can assign the LAN port to this and we should notice that the port should touch the both side of the metal. And then we should define the analysis setup and the frequency sweep. And finally we should assign a radiation boundary, a sphere, which is lambda over 4 from your loop. Let's move on to HFSS. So, and define a small electric loop antenna. Let's draw a circle in a XZ plane. Let's say 5 in the center position of the circle, Y direction, yes, the radius 0.5, let's say, number of segments 0, and now we'll on the Z direction we sweep it. Now we have a very beautiful torus right now. Now we can draw a box to have a port position. We can modify the box. Let's say for minus 0.5 and again minus 0.5. X size is 2, 1, 1. Yes. It should be small enough, so let's say in the Y direction, let's say minus 0.25 and yes. So we subtracted 2 boxes to try, and now we subtract them. Circle 1, subtract from box 1. Okay. And now we can define a port. For defining a port, for defining a LAN port, we should draw a rectangle in XY plane. And now define the geometry of the rectangle. So let's say again for minus 0.25 and minus 0.5. Let's say the X size 1. Let's see, 101. Nope. Oh, it should be 0. Now let's say the position of the feet is 4 minus 0.25, 0. In the z-axis direction, x size is equal to 2 and the y size is equal to 0.5. And now we can define the LAN port by clicking on the sheet. Right click on the sheet, assign excitation, LAN port, and here you should define a new line of the LAN port. You should now see the triangle. It indicates you are in the middle of the sheet, middle of the line, sorry. And here are again you are in the middle of the line. Now it's defined. Let's renormalize the video. It's finished. And now you can see the port field here. Oh. Now I think we should assign a material first. Assign a PC. Now let's move on and create a boundary condition of this small electric loop. For drawing a boundary condition, we should draw a sphere with the radius of lambda over 4. We designed a loop for f equal to 1 GHz for the frequency of 1 GHz, which the lambda is about 300 millimeter, and the lambda over 4 is equal to 75 millimeter. Now we can right click on this sphere and assign a boundary condition, radiation. Now we can go to the simulation boy and validate our design, or we should define an analysis setup. Going to the analysis setup and using advanced mode. So we want to have an adaptive solution with a frequency of 3 GHz. We want to solve our simulation in a single frequency 3 GHz. Maximum number of pass, let's say 10, and the maximum delta H is good. Let's say 0.01. Going to the option, and minimum number of pass, let's say 3, and minimum converge pass, let's say 2. And for if you want to see the electric field, you should save the fields at each frequency you want to see. Now also we can frequency sweep. Let's say, yes, it's good, 1 to 6, and the sweep type is interpolating, is good for us. Now we can solve it, can validate it, and now we can solve it. Or we can right click on to analyze, or we can analyze it. As you know, the electric small loop antenna has the inductive performance, and the imaginary part of the input impedance and should be the positive, and it indicates that it has inductive performance. It can be compared with the negative imaginary part of the small dipole, electric small dipole antenna, which it is a capacitive performance, and this small loop have an inductive performance. Now let's move on to HFSS and see our input imaginary part of our impedance. As you can see here, we define the far-field infinite sphere, and also we can see the surface current of the loop, and we can see the radiation pattern of the electric small antenna and a 3D radiation pattern. Sorry, I made a mistake, or I should define a frequency at 1 GHz and sweep frequency from 0.5 to 4 GHz. Now let's see the result, the radiation pattern, and the imaginary part of the impedance of this small loop antenna. Go to the result, right click on the result, and create a model solution data report, rectangular plot, Z parameter, and select the imaginary part of the Z parameter, and the primary sweep is from the frequency, all frequency. We can see the imaginary part of the Z11, and you can see the imaginary part of the Z11 is positive, and it says that our small loop is have a inductive feature. At 1 GHz, can select a marker, add marker at 1 GHz. You can see under 1 GHz is about it's about 100 HONB. Oh, it's 100 ohm, yeah. Let's go to the results and see the radiation pattern. Create a far-field report, rectangular plot, or you can see on the radiation plot, or you can see go to the result and radiation box and see the magnitude or angular plot, gain total, let's say dB. Have a new report. We can choose which cutoff this 3D pattern. Let's say phi is equal to 0 is the x-plane cut, and C phi equal to 90 degrees, the y-plane cut. You see the y-plane cut and the x-plane cut are equal to each other. Also, you can have a radiation field, far field, 3D polar field, k into dB. You can see the Donald-Check radiation pattern. Also, you can see this radiation pattern along your structure. Hide the sphere. You can see the small loop. Right click, plot field, radiation field, and our gain plot is number 4. Transparency is 0.8, and the scale is to be 0.1. And now you can see the radiation pattern, Donald-Check of the small loop antenna. In this tutorial session, we have learned how to create a fundamental 3D models in HFSS and how to design and create a simulation of small loop magnetic dipole antenna, and see the result and create a far field pattern of each antenna. Thank you, take care.